14.5, probabilities of various combinations. Essential question, how do you calculate the number of different combinations containing R elements taken from a set containing N elements? So we'll start off with the definition of combination. A combination is a bit different than a permutation. So in a combination of elements in a set is a subset of those elements without regard to the order in which the elements are arranged. So without regard to order. Permutations cared about order. Combinations does not. So I'm going to try and differentiate for you the difference between a combination and a permutation using this next little example here. So there are 24 different 3-letter words that can be made from the 4 letters A, B, C, and D. So what you can see here is you have these 24 different words, 3-letter words that can be made. Okay, well that's the number of permutations. Okay, so this right here, the 24, is the permutations. But as far as combinations go, we don't care about the different order. So ABC would be the same as ACB, BAC, BCA. Those are all the same in the world of combinations. So that's just one combination. So we have a total of 4 combinations here. Okay, and that's basically what this says, but I'm going to go ahead and read through it just so that we can, clarify it. So because these words are arrangements of the letters in definite order, each is a permutation of 4 elements taken 3 at a time. So if you remember, this was 4 elements taken 3 at a time. And you know how to calculate that hopefully by now. So this would be the same as 4 factorial over, and then we take the difference of these. So 4 minus 3 is 1 factorial. Or in other words, this is going to be 4 times 3 times 2 times 1, which is 12 times 2, which is 24 total permutations. Okay, so that matches with that. Now suppose you are concerned only with which letters appear in the word, not with the order in which they appear. For instance, you would consider ADC the same as DAC. To be the same. I can't read. Because they have the same 3 letters. Each different group of 3 letters is called a combination of those 4 letters. Okay? So, symbols for combinations, we do NCR, right, which is the number of different combinations of N elements taken R at a time, pronounced NCR. And then for permutations, we do NPR, which is the number of different permutations of N elements taken R at a time, pronounced NPR. Okay, and then here's the math behind it. So the calculation of the number of permutations or combinations. So they work very similarly. There's a little bit of a difference here. So when we have 9p4, this is really 9 factorial over 9 minus 4 factorial, which gave you the 9 factorial over 5 factorial. Okay, so that one you should be pretty used to. And if you wanted like an actual definition, we did NPR. And that's basically the same as saying I'm going to do n factorial over n minus r factorial. Okay, so that's for permutations. And then for combinations, so this right here, notice they've got 9 factorial over 4 factorial times 5 factorial. Okay, so what you do here, take the 9, and we do 9 factorial on the top. And then basically you do, this is 4 factorial, so that's the same. And then you take the difference of them, 5 factorial, which is why you get such a smaller number, because you're dividing out more. Notice in our previous example we had 24 permutations. we had 4 combinations. That's because we end up dividing out more numbers. Okay, so this ends up giving you, this is basically, so for combinations we'll do NCR, and that's basically you do the n factorial on the top, then you do the r factorial down here, then you take the difference, it's n minus r factorial. Okay, and you're going to want to also know that one. All right, so let's calculate 4C3. Okay, so for this, I'm just going to say, okay, I do 4 on the top. On the bottom, I'll do my 3 factorial, and then I'll take the difference, and I'm going to go ahead and write it out, even though it doesn't matter. 4 minus 3 factorial. Okay, so this would be, let's see, I'm going to go 4 times 3 factorial over 3 factorial times 1 factorial. And these reduce out, and I should just be left with 4. Which is exactly what our last problem was, right? So, or our first example here. This was, I had 4 things, and I wanted to arrange them 3 at a time, and order did not matter. So there were 4 different combinations, okay? Not permutations. Now, you can also do this on your calculator. So on my calculator, let's see, I'll do it both ways for you guys. Let's see, mode, I'll start with my math print. Okay, so you go math, probability, and then it's that number 3 right there. And so if you have one of these TI-84 plus calculators, then it's pretty simple. You just would put in, let's see, we've got 4 and 3. Now, if you don't have that, you have one of the older ones. Let me go up here, classic. Okay, so I'm going to do the exact same thing though. Math, probability, number 3. Oh, I did it wrong. I have to, just kidding. You have to put in the first number first. So I would do 4, math, probability, and then 3. And I get the same exact answer. Okay, so on your calculator, this is under math. Then you go to probability. And then, oops, not probability. And then you go to number 3. Okay, a lot of really good things are located under math. All right, example 2. We're going to write 9p4 as a ratio of factorials. Interpret the answer in terms of the number of elements in the set and the number of elements selected for the permutation. Okay, so let's start with writing out 9p4 as a ratio. So basically what they're saying is do it like this right here, right? That's a ratio. So this is going to be 9 factorial. So basically I have 9 things. I'm going to choose 4 of them at a time, and order matters. That's what this is saying. So I have 9 elements in my set, and then I'm going to I'm going to subtract those, because basically what's happening now, 9 is the number of elements that are in my set, and then 5 are the elements that, because I'm choosing 4, so it's 5 of those elements that I don't really care about selecting, right? So this is the number of elements in the set. And then this is the number of elements not selected. And that's what I'm dividing out. All right, so I'm going to go ahead and evaluate this by hand, because as long as I wrote out the ratio, I might as well do it. It's actually quite simple. So you go 9 times 8 times 7 times 6 times, I'm going to stop at 5 factorial because I have a 5 factorial in the denominator. Right, so those reduce out. Okay, so let's see. Interpret the answer in terms of the number of elements in the set and the number of elements selected for the permutation. So I think that we have that. We've talked about what the number of the elements are in the set, the number of the elements that we did not select, our total answer here would be 3,024. And you could do this another way. So you could say to yourself, I have 9 things. So when I choose my first thing, I have 9 different options to choose from, right? So you could say, if I want to choose 4 different things, I could be like this. Let's see, do I have enough room here? Right? So for the first thing, I have 9 options available to me. Okay. Now, when I choose my second thing, I've just got 8 options available to me. Choose my third thing, I got 7 things. Choose my fourth thing, I have 6 things. Which, basically, these are the exact same thing, right? Okay, so these match up. So 2 ways of going about finding those number of permutations. All right, let's do example 3. All right, so now we're going to write and choose 4 as a ratio of a factorial to a product of factorial. As a ratio of a factorial to a product of factorial. So in the top, we're going to have a factorial. In the bottom, we're going to have a product of factorials. Notice how I had to read that a couple times to try and figure out what they were asking? Yep, that happens. Interpret the answer in terms of the number of elements in the set. Well, we already know how many elements are in the set. It's going to be 9. And the number of elements selected for the combination, which we know is 4. Okay? All right, so 9C4 is basically going to be 9 elements that are in my set. Then they do have us divide out the number of elements that they selected, as well as the number of elements that did not get selected. So that's that 9 minus 5. Oh, sorry, 9 minus 4. So now I've got 9 factorial on the top, 4 factorial times another 5 factorial. Okay, so this right here is the number of elements in the set. Okay, this is the 5 was the elements that were not selected. And then this one right here is the number of elements that were selected. Oops, I'll put number. And then if we continue to calculate this, so I would do, let's see, I'll go back to that 5 factorial. So 9 times 8 times 7 times 6 times 5 factorial. And then here I'm going to have, 4 times 3 times 2 times 1. I'm not going to put the 1. And then I'm going to leave the 5 factorial. So the 5 factorials here reduce out. Looks like I've got a 6 here. Reduce that with the 6. The 4 can definitely go into the 8 2 times. So what is that going to be? 63 times 2, 126. So 126 ways or groups of things that if I have 9 things and I choose 4 of them from those 9 things, I want to take 4 of them at a time, there's 126 possible different combinations. Meaning order doesn't matter. Okay, example 4. In how many different ways could you form a committee of 3 people from a group of 7 people? Explain how you know that a number of combinations is being asked for, not a number of permutations. Okay, so if you form a committee of 3 people, then that means that I want to have, basically I have 7 people right now. I want to choose 3 of those people. So, number of ways that I can choose 3 people is basically the same as saying 7C3. Okay, let's go ahead and we'll get that number and then we'll do the explanation in a few minutes. So this becomes, the math is pretty simple. Once you get used to this, it's just, Yep, 7 factorial, 3 factorial, take the difference, 4 factorial. Okay, and then I'll say, oh, this is 7 times 6 times 5 times 4 factorial over 3 times 2, which is really 6, times that 4 factorial. 4 factorials go away, the 6 goes away, and I'm left with 35. Okay, 35 what? So let's read this one more time. In how many different ways could you form a committee of 3 people from a group of 7? Okay, so this is like the number of different types of committees, I guess I could basically have. So 35 committees. Explain how you know that a number of combinations is being asked for, not a number of permutations. Okay, well, if I have a committee with 3 members, those 3 members, no matter what order I put them in, it's still the same committee, right? So committees with the same members are different only if the members have different roles. And nobody talked about different roles here. So it'd be one thing if I was looking for like a president, a vice president, and a treasurer. But none of that was specified here. So I'm going to say something like, do I know how to spell committees? Is that how you spell committees? Ooh, I don't know. We'll come back to that. Committees with the same members. Nope, 2 T's. I could have cheated and just looked up there to begin with. All right, there we go. There's a lot of doubles in committees. All right, committees with same members are different only if the members have different roles. And there will be times like that, right? Where it's like, you know, how many different ways can you choose a committee with a president, vice president, and a treasurer? Oh, look at that. Probably this next problem is the one. All right. Example 5. If a committee of 5 is selected at random from a group of 6 women and 3 men, find the probability that it will include. So now we're talking about probability. Okay, so that means I need to have, you know, the number of favorable outcomes out of all the total outcomes. All right, so let me just see what we were doing here. So we've got 6 women and 3 men. So I've got a total of 9, right? So selecting from a total of 9, just writing myself some notes here. And I'm selecting 5. So let's figure out what my total sample space is. Because remember, we're going to have to divide by that in order to get a probability. My total sample space will basically be I have 9 people and I'm choosing 5 of them. Okay? All right, so let's see. This is just going to give me 9 factorial over 5 factorial over 4 factorial, which I feel like we already did this number somewhere, 126. Yep, I think it was example 3. So that's going to be 126. So I can have 126 different possible committees. All right. Now, let's go through and answer each one of these, because now we're finding the probability. This is our sample space. We're going to find the probability of Eileen and Ben are 2 of the 9 people. Okay. So A, probability that we've got Eileen and Ben. So basically that means I want the number of Eileen and Ben being chosen over the total number of the sample space, right? All right. So to figure out the number of ways that we can choose Eileen and Ben, well, really there's only one way to select Eileen and Ben. And then you have to select 3 other people, right? So this would basically be there's one way to choose Eileen and Ben, And then you're also going to, out of the 7 people that you have left, right, because you have 9 people total, you choose Eileen and Ben in one way. Okay, and then you have 7 people left, and you need to choose. Well, we had a total of 5 that we're selecting, so there's 3 left to select. Okay, and when you do this, let's see, I'll just go ahead and I'll use my calculator on that one. Go back to my math print mode. Practice it both ways. Make sure you can use your calculator, and then also make sure that you can do it by hand using those ratios. So this would be 1 times 35, or 35. Okay, so this is the top, and then on the bottom, my number of sample space is 126. So I'm just going to go ahead and put that on the bottom, because I'm calculating probability. And then if I do 35 divided by 126, I get about 27.777%, or how about we go with about 28%. All right, so that's A. Maybe I should write you guys a little note here. So here, we chose that 1 because there's just one way to select Eileen and Ben. Then you select the other 3. So this is one way to select. Oops, not so. Okay, well, my spelling's not good today. Select Eileen and Ben. Then select other 3. Right, so I select Eileen and Ben, and I select the other 3 people. And the order there doesn't matter. All right, let's look at the next one. So, for B, we want exactly 3 women and 2 men. Okay, so we want the probability that we have 3 women and 2 men. Oh, man, spelling, I don't know. All right, so I want to figure out the number of ways that I can choose 3 women and 2 men over the total number in my sample space, which we already have that. We did that in the very beginning. It's 126. Okay, well, the number of ways to choose 3 women and 2 men, well, let's see, there's 6 women, and I want to choose 3 of them. So that's 6C3. And I also want to do 2 men. There's 3 men, so I'm going to do a 3C2. And you can do that right in your calculator. You can also multiply it out. Oops, what have I done? Got to be able to do your calculator, though. That's the only problem. Okay, so I'm going to do 6C3, and then I can multiply that by, no, I'll do it again. Some of you guys, again, if you have that older calculator, you're going to have to do it a little bit differently. You have to put in the number in the set first. Then I get 60. Oops. Now that's just for the numerator, because probability, so it's got to be out of the whole sample space. So I'm going to actually take that 60 divided by 126 and get 47.62%. We'll go ahead. Your book has been rounding these up, so we'll just go to 48%. Okay, and then the last one, C, you have at least 3 women. So this is the probability of at least 3 women. So that really means I could have 3 women, 4 women, 5 women, right? I think, could I do 6 women? Nope, because there's only a committee of 5. So you do 3 women, 4 women, or 5 women, right? So I need to figure out the number of either having 3 women or 4 women. Oops, I should put more. Or 5 women. And that will be all over the sample space. Which again is 126. Okay, so now I already wrote it down, so you guys were probably like, oh, Frisk, what are you doing? So when we do the number of 3 women, okay, we're going to add that to the number of 4 women, and then add that to the number of 5 women because we have the or here, right? Okay, so those are really plus signs. Okay, so now I think actually I'm going to go off to the side here and I'm going to calculate each one of these separately. So let's start with, if we have 3 women, so the number of 3 women, well, how many men will I have? I'll have 2 men. I shouldn't use that. I should use and. Well, I think we just did that one, right? So that was a total of 60. Now I can also have 4 women and 2 men. Nope, I lied. 1 man. So now, I'm going to do basically the exact same thing that I did here. I'm going to have 6 women, but I'm going to choose 4. And then 3 men, I'm going to choose 1. Okay? So this is 6 women, choosing 4 of them, times, and there's 3 men, and I'm choosing 1 of them. And I'll just go back into my calculator. Let's see, can I actually just go up to here? Let's do this. And I got 45 for that one. And then my last one is if I do 5 women and 0 men. So once again, I'll do the 6 choose 5 and the 3 choose 0. Which really, this just becomes 1 because it's going to be 3 divided by 3. Did I do that right? 3 divided by, let's make sure that I'm right about that. Yep, okay, good. Just making sure. Had to think about it. It's been a while. Okay. So for this one, let's see, I'm going to go back up here. I'll use that same information. 6 choose 5. And now really that's just 1, but since I already had it. So that's 6. Okay, so back to my probability then. Let's go back here. So for this, it's now going to equal, well, this top part is going to be 60 plus 45 plus 6 all over, and then the bottom part is 126. That's 111 over 126. About 88.1%. They're rounding in the book to about 88%. Let's see, do we have more? We do. All right, Pascal's triangle. We talked about this in Algebra 2. So Pascal's triangle, the reason I'm bringing this up is because actually every entry into Pascal's triangle is actually a combination. Now, we use Pascal's triangle to help expand binomials. So, for example, if you have a plus b raised to some power, like squared. Well, you should be able to do this one pretty quickly in your head, but it becomes a squared plus 2ab plus b squared. And that's pretty easy. You're able to do that one. But what if I gave you like a plus b to the 9th power? You would have a pretty hard time knowing what these coefficients were, and nobody expects you to multiply that out 9 times. So that's where the Pascal's triangle really comes in handy. All right, so Pascal's triangle looks like this. It's basically starts at the top with a 1, and then you start building this pyramid of 1s on the outside. So I'm going to go down again. Now, anytime I'm in between two numbers, I sum those two numbers. I'm going to keep going. So 1's on the outside, sum the two numbers, sum the two numbers, 1's on the outside. 1's on the outside, sum the two numbers, sum the two numbers, 1 on the outside. I'll do this a few more times because it's fun. You could do this all day long if you wanted to. Let's do one more. 21, 35, 35, 21, 7, and 1. Okay, and you could, like I said, you could keep doing this. Hopefully you won't need to do it for too long. So this right here, this is going to be your coefficients if you, for example, had a plus b to the 0 power. Right? It's always a binomial. This also works for subtraction. You just alternate the signs. You'll have a positive, a negative, a positive, a negative. Okay, this one would be if you had a plus b to the 1st power, because the coefficients of a, this would be a plus, so 1a plus 1b. This one right here is for a plus b to the 2nd power. So let's see how this corresponds with this. Notice the coefficients. Coefficient of your first term is 1. Coefficient of your second term is 2. Coefficient of your third term is 1. Okay, moving on, this would be a plus b to the 3rd. Okay, so basically, we call this, you want to think of it like this is row 0, and that means 0 to the 0 power. Okay, this would be row 1 for the 1st power. This would be row 2 for the 2nd power, and so on. Okay, and these just keep going. So then this would be a plus b to the 4th. I'll show you how to do these two. 5th, and so on. Now what's kind of cool is that every single place in here, which is why we're bringing it up right now, is actually a combination. Okay, so the first one is that you are in the 0 row C0. Okay, so if you do, actually I could just do it here. Well, if you do math and you do 0, choose 0, you get 1. Okay, so that might be something to memorize. Okay, then next one, I'm in the 1st row. I'm going to be in the 0 position. 1st row, 1st position. Now watch this. So same thing is happening here. So these are all equal to 1, but this is 1, choose 0, you get 1. Or 1, choose 1, you also get 1. Okay, now I'm going to go down to the 2nd row. I'm going to choose my 0 position. 2nd row, my 1st position. 2nd row, my 2nd position. Okay, so again, this is going to give you a 1. This is going to give you a 1. Guess what that's going to give you? It's going to give you a 2. Just if you don't believe me. I'm not going to do this for all of them, but they totally, every single one comes from a combination. So there it is. There's your 2. Oops, the sun is shining crazy. So hopefully you guys are getting a good view of this one. My computer. All right, and then like the next one would be, okay, now I'm in row 3, choose the 0 position, row 3, choose the first position, row 3, choose the second position, row 3, choose the third position. Again, these are going to be 1s, and then these are going to match. It's going to be 3 and 3. And you can do that all day long. So all of Pascal's triangle, every single entry is basically what row it is, what position it is. And we start everything with 0. Okay, so let's actually apply this. So that's all just fine, Frisk, but let's actually apply this. So what if I gave you a plus b to the 5th power? All right, well, I know it's the 5th power, so I would go down to the 5th row. And usually when you make the Pascal's triangle, you're not going to sit there and like label this all out. So you go 0, 1, 2, 3, 4, 5. Okay? All right, so now you always start with A. You give the first term all the powers. So then B gets none of the powers. And your powers have to add up to this power all the time. So this would be, well, first of all, my coefficient is 1. A to the 5th power, B to the 0 power. Because it's plus, we don't really worry too much about the signs. Now my coefficient for the second term is 5. A gets 1 less power, so it's 4. B gets 1 more power, so it's to the first, and they have to add up to 5, because that's the power. Keep going. Coefficient now is 10. A gets 1 less power, B gets 1 more power. See how they still add up to 5? Next term, coefficient is 10. A gets 1 less power, B gets 1 more power. They still add up to 5. Next coefficient is 5. A gets 1 less power, B gets 1 more power, still add up to 5. Last term, coefficient is 1. A has no more powers, and B gets all the powers. Now, I wrote that out. If I was doing this, I wouldn't write some of this stuff out. So, for example, I would not have B to the 0. I would not have a 1 there. So this would just be A to the 5th plus 5A to the 4th, B, plus 10A cubed, B squared, plus 10A squared, B cubed, plus 5A, B to the 4th, plus, and then I'll just go B to the 5th. Now, if this was subtraction, you'd have the exact same terms, but your signs will alternate. First term's going to be positive, negative, because just think about the sign there. Okay? What that would do if you multiply this out 5 times. Nobody wants to multiply this out 5 times, though. So I would always use Pascal's triangle for this. Then there's also the binomial theorem, and we'll get to that. Okay, so moving on, we're going to introduce you to the binomial theorem, which, again, you can use Pascal's triangle to do a lot of this, but if I had asked you, for example, to do A plus B to the 999th power, I don't think you want to make Pascal's triangle all the way to 900. Actually, it would be the 1000th row, right? So instead, let's introduce you to some of this information that we never did in Algebra 2, so we'll talk about it now, and then we'll use it a bit. Okay, so you can use summation notation to write a series. So this right here, this is what we call a finite series. Okay, this is a finite series, meaning it ends. An infinite series would not end. So if we had 3 plus 6 plus 9 plus 12 plus 15 plus on and on and on, that would be an infinite series. This one ends, so it's a finite series. So we call this summation notation because this is actually, the sigma here is like a summation symbol. Okay, so for example, for the finite series shown, well, here, you can write this. 3 plus 6 plus 9 plus 12 plus 15 is equal to, and now this is the summation, from I equals 1 all the way to 5 of 3I, where I is the index of summation, 1 is the lower limit of summation. Okay, so this is like what place you're on. Remember how I was like place 0, place 1, place 2, right? here, how I was like place 0, place 1, and so on. Okay, so this would be, for example, here, this would be your first term. So I equals 1. This would be your second term. This would be your third term, your fourth term, your fifth term. Okay, of this. And 5 is the upper limit of summation, which means we should only have 5 terms total. And in this case, the summation notation is read as the sum from I equals 1 to 5 of 3I. Summation notation is also called sigma notation because it uses the uppercase Greek letter sigma written as an uppercase sigma. All right, and then summation notation for an infinite series, this is what I was talking about, is similar to that for a finite series. For example, here it is. For the infinite series shown, well, actually down here, this is infinite. Notice how it goes on forever. It's got that dot, dot, dot. You can write, instead of saying like from 1 to 5, you'd say from 1 to infinity of that same function or expression. The infinity symbol indicates that the series continues without end. Okay, let's go back up to the finite. Actually, for both of these, it really doesn't matter. But really what this is saying is, okay, this is my first term, my second term, my third term, my fourth term, my fifth term. Now, how do I get these numbers? Well, I take 3 times the term number, right? So this is 3 times 1. I take 3 times the term number. This should be the second one. 3 times 2, that's my term number. This would be 3 times 3, this would be 3 times 4, and this would be 3 times 5. Okay, so that's summation or sigma notation. And the reason I'm introducing that to you, you'll see this in a lot of definitions. Okay, so the binomial theorem, this is a way that would make this a little bit easier for you to do without having to draw out Pascal's triangle. You definitely need to use a calculator, however. So this is the binomial theorem. And basically, if you have the expansion of any binomial for any positive integer n, okay, so we're talking about when you have a positive exponent, is this. For a plus b to the nth power, notice you've got these combinations here, right? So it's like whatever row you're in, right, whatever power you are, and then you're going to choose 0, then choose 1, then choose 2 for every coefficient of every single term. Now, the a term, that first term in your binomial, always gets the most powers, which is at n. And then the second term starts with 0 powers. And as you move on to each term, right, this 0 is going to increase to 1 and 2 and 3 and so on. Your power of your first term is going to reduce by 1, and your power of your second term is going to increase by 1 every single time. So now this would be, instead of n minus 1, if we're decreasing it by another degree, we're going to do n minus 2. And then this is going to go up, right? So this is constantly increasing the second term. And then they summarize this using a summation. They say when from r being 0, right, which is basically what's happening here, r is 0. Okay, and then we just keep going up until n, until however many terms we're supposed to have, whatever degree this is. Right, so you would end up with this combination, which ends up looking just like this, until however long you're supposed to go, and then n minus r, and then b to the r power. Okay, so maybe try and spend some time thinking about that. But for the most part, I'm not going to use the binomial theorem. I'm going to use Pascal's triangle because it's super easy, unless they gave me something really, really complicated. But it's important that you understand that it's out there, that binomial theorem. Okay, so let's do some more complicated ones. So we got x plus y to the 6th power. So this is actually not too complicated. It's very similar to like our a plus b to the 5th power. We're just going to go down one more row. Right, so we're going to use these coefficients, the 1, 6, 15, 20, 15, 6, and 1. Okay, so, and then using the binomial theorem, if I wanted to do that, really, for my first one, it's going to be 6 and 0. A to the 6th. A, here's my x. B to the 0. Y, here's my b. Okay, so this is really going to be 1, or in other words, and I'll write this using the binomial theorem too. 6, choose 0. And then this would be my first term, which is x, to the 6th power. It gets all the powers. And y gets nothing. I'll write it all out for you guys. Okay, now for the next one. Now I know this from Pascal's triangle. Right, 6, 15, 20. Okay. But if I didn't know that, then I would go, okay, I got 6 things, right, 6 degrees. And now I need to go one further because it's my next term. Right, so I'm just following this pattern. And then my x, or my first term, gets 1 less power, which is exactly what this is saying. My second term gets 1 more power. See how that's increasing? Okay, the next one I think was 15. And again, that would come from 6, C, now you're at 2. X gets 1 less power, Y gets 1 more power. So the next one is 20, and then I just go down. Some of them double. It's like every other one there's double, and then every other one there's not. I think that has to do with evens and odds amounts of terms. Okay, so this is going to be, what I say, 20. And that would be the same as 6C3. If you don't believe me, you can go ahead and double check that. X gets 1 less power, Y gets 1 more power. And make sure that they're always adding up to give you that total power there. 15, X gets 1 less power, Y gets 1 more. 6, X gets 1 less power, and Y gets 1 more. And then the last one is 1, and X gets no powers, and Y gets all the powers. So if I simplify this, this would be x to the 6th plus 6x to the 5th, y plus 15x to the 4th, y to the squared, plus 20x cubed, y cubed, plus 15x squared, y to the 4th, plus 6x, y to the 5th, plus y to the 6th. Way quicker than going x plus y times itself 6 times. Okay, moving on. This one will be a little bit more complicated because your terms now are not just a single factor, right? They're made up of several factors, okay? Nonetheless, though, think of this still as like, hey, here's my first term, A. Here's my second term, B. Okay? Now this is to the 4th power. So because it's such an easy one, I would just go straight to Pascal's triangle, and it's 1, 4, 6, 4, 1. I think I'll write that down. Those are going to be my coefficients. Okay, so, and these coefficients again come from combinations. So this would be 4, choose 0. This would be 4, choose 1. This would be 4, choose 2. This would be 4, choose 3, and 4, choose 4. That's where those all come from. So if you don't remember Pascal's triangle, you can go in and you can calculate those. Okay, so we're going to start with our A here. Our first term, which is A, gets all the powers. Our second term, which is this, the 2b cubed, gets none of the powers. And our coefficient was 1. I'll write all that out for you guys. And it's an addition sign, so they're all going to be plus. Hopefully I gave you an example with a negative. Let's look. All right, next one. Start with your coefficient, which is 4. First term gets 1 less power. Second term, now I'm writing these in parentheses because you're going to raise that to a power. In this one, it's not that big of a deal. I'm going to raise it to the first power. But that power needs to be given to every single thing in this term. Okay? Next coefficient is 6. Okay, a gets 1 less power. And then the second term, the 2b cubed, gets 1 more power. Next coefficient is 4. And if you don't believe that this actually works, be my guest, multiply that out 4 times. It'll take you forever, okay? So this is just a quicker way of doing this. So we've got 4, a gets 1 less power, so it's a to the first power. And then the 2b cubed gets 1 more power. I got 1 more here. Coefficient's 1. A gets no powers because it gets less powers. And then the 2b cubed gets all the powers, so it's 4. Notice how they always add up to whatever that degree is. All right, so just simplifying a to the 4th plus, okay, this is where it gets, a little bit more complicated. So this one's going to be easy because this is still going to be 8a cubed b cubed. But now I'm going to slow it down a little bit, and I'm going to start taking care of these exponents first. So I have 6a squared times, and that's going to be 4b to the 6th. Then I got 4a, and that's going to be 8b to the 9th. This is just going to be 1, and then that's going to be 16b to the 12th. All right, so I'll simplify one more time. A to the 4th plus 8a cubed b cubed, 24a squared b to the 6th, 32a times b to the 9th, and plus 16b to the 12th. There it is. Or you can multiply that thing out 4 times. Now let's do one with a subtraction sign in there. Same power. We'll just put a subtraction sign in there. That way you can see what's happening. All right, so I'm going to think of this. X is like my A. And then my B, actually I'm going to rewrite this. Because really, this is x plus negative 5 to the 4th, right? So we'll make x our A, and our B here is going to be negative 5. We're going to use the same coefficients, 1, 4, 6, 4, 1, because it's to the 4th power. So you'd want to go to the 5th row down on Pascal's triangle, right? Because we start with row 0. So actually the 4th row down, but if you're counting, it's 5 rows down. Okay, and then we just do the exact same thing that we just did. So it's going to be 1, and then x gets all the powers. And then our b, which is negative 5, gets none of them. Okay, plus, and I'm just writing it, like as you get better at this, I would not continue to write out stuff that you know is like equal to 1. Now you're going to do 4, which is my second term coefficient. X gets 1 less power. Negative 5 gets 1 more power. See, and that negative now is going to come out here and make this a negative. So they're going to alternate. It's going to be positive, then negative, then positive, then negative. Okay. All right, then I'm going to go 6. X gets 1 less power. Negative 5 gets 1 more. 4, x gets 1 less power. So now negative 5 is up to power of 3. Plus 1, x gets no powers, and negative 5 gets all the powers. All right, so this becomes x to the 4th minus, now this is 20x cubed. Okay, this is where I'll start simplifying my exponents first. So plus 6x squared times a positive 25. Okay, and then I'll do the same thing here. So this is going to be 4x times, that's a negative 125. That just becomes 1, so it's negative, oh no, that's going to be positive 625, I believe. Okay, simplifying one last time. Let's see, that's 150, I believe. That's 500, but negative 500 and positive 625. Hopefully this isn't too challenging for you. Hopefully you're kind of getting the hang of this. Do one more of these. This time we'll keep the subtraction sign in there. And now our both of our terms here, none of them are just like to the first power or just basically by themselves. So I'm going to first rewrite it so that I can see that this is really the same as 2x plus a negative y squared. Okay, and so negative y squared is really your b, and all of that is raised to the third power. So this part here is like your a, this part here is like your b. And if I go to the third row on Pascal's triangle, okay, that's really, and really that's 1, 2, 3, you got to go 4 rows down. Your coefficients will be 1, 3, 3, and 1. And then I just get started. So coefficient's going to be 1, then that's 2x, and that 2x gets all the powers, so that's 3. Okay, and then the b, or your negative y squared, gets none of the powers. Plus, okay, and now my coefficient's 3. My first term is 2x, which now gets 1 less power. Well, my second term, which is negative y squared, now gets 1 of the powers. Got another 3 as my coefficient. And then 2x gets 1 less power, while the negative y squared gets 1 more power. Last coefficient is 1. Now the 2x gets no powers, and the negative y squared gets all the powers of 3. Okay, so simplifying, this is going to give me 8x, because that's just 1. Okay, let's see here. So you want to do all your exponents first, so that's what I'm going to do first. So this is going to be 3 times 4x squared and a negative y squared. 3 times, and that's still just a 2x. Now, I'm squaring the negative, and I'm squaring the y squared. So that's going to be a positive now. So it's going to be y to the 4th. This just becomes 1. Now, that's going to be cube that negative, which is still negative, and then y to the 6th power. So I think we should end up with 8x. This will be negative. Negative 12. You can put plus negative, but I'm just going to put minus. 12x squared, y squared. These are all positives. We'll get 6x y to the 4th. And this will be negative y to the 6th. So see how whenever you have that negative in the middle, you alternate signs. Okay, I think, yes, last one. Yay! I know this is a long lesson, but I'm giving this to you over a few days, so you should be good. All right, find the coefficient of x to the 7th in 2 minus 3x to the 10th. Okay, so I'm going to rewrite this like I always do. For 2 plus, and this is really a negative 3x all to the 10th power. Okay, so what I'm thinking about is, if you're thinking about your Pascal's triangle, you're thinking about your 10th row and the 7th term over, right? So this is really to find the coefficient of just that term. You really are just going to do 10C7. So this right here will give you just the coefficient. So that's going to be 10 factorial over 7 factorial, and then take the difference of them, 3 factorial. or 10 times 9 times 8 times 7 factorial, 7 factorial over 3 times 2. And you could, of course, use your calculator if you wanted to. But this is going to be, let's see, this is pretty easy. So 12 times 10 is 120. So that's your coefficient of the term. All right, so we're going to do 120. Now we're 7 in. So originally, here's your first term, and here's your second term. Right, so this will be your A, this will be your B. Okay, so we're 7 in here, x to the 7th, right? So we need this x to be, we need this to have a 7th power, which means that this is going to have a power of 3, right? Because they need to add up to 10. Does that make sense? Or this one's going to have the 7th power. This one's going to then make up the difference between 7 and 10. So 3. So you're going to have 2 cubed. And then negative 3x to the 7th power. Oh, I guess all I needed was the coefficient. Well, let's find the entire term. The question just asked for the coefficient. There's my answer. Let's find the entire term, though. Why not? This is super fun, isn't it? Okay, so this is going to be 120 times 8 times negative 3 raised to the 7th is negative 2187, and then x to the 7th. So multiplying all those together. Ooh, okay, what is that? So negative 2,099,520 times x to the 7th. So that would be if they asked to find the actual term. This is the coefficient, so we answered the question just over here. Sorry about that. This would be the actual term. So we did a little extra work, but that was fun.